say a little bit about particle collisions around black holes in magnetic universes. But first, let me acknowledge that this talk originates from my master thesis that was supervised by Jiří Bičák. And now to the talk. Let's say something about the motivation. There are many examples of high collision energy phenomena for particles colliding in the vicinity of black holes. But those phenomena are mostly considered in vacuum, like the first one, which was described by Biagos, Silk and West, and so those phenomena are referred as BSW effect, or as in this case, generalized BSW effect. As I said, those phenomena are mostly considered in vacuum, but astrophysical black holes is to be surrounded by accretion disk and by strong electromagnetic fields, and it is almost impossible to model this situation in advance. But I turn to so-called MKM class of solutions. Those are exact solutions of Einstein-Maxwell system of equations, and they describe a black hole, isolated black hole that is immersed in an external, arbitrarily strong magnetic field. Well, the calculations in this class of solutions, they are rather involved, but using some tricky methods like near-horizon limiting descriptions, we managed to treat at least extremal cases, and I think that we achieved some other interesting results, like that we unified some known results for Kerr-Newman class, and we found relations between more theoretical works that are dealing with the geometry of degenerate horizons and with astrophysical works that are dealing with magnetic fluxes. Well, so what is our basic setup? We model a black hole with axially symmetric stationary metric. Here is the Leb's function, and here is the dragging potential. For the test particle, the charged test particle, we use canonical formalism with this Lagrangian and this canonical momentum. Because of the symmetry that we assume, some components of the canonical momentum are conserved during the electrogeodetic motion. And these are energy and actual angular momentum. I use the specific constants divided by rest mass, and so I do for the charge. Many of us do so. Now, from the symmetry and from the existence of the mentioned two constants of motion, one can get two first-order equations of motion, and when we impose additional symmetry, the reflection symmetry, which is quite natural for the black hole spacetimes, when we start in the equatorial plane and when the velocity is also pointing in the plane, the particle has no reason to deviate to one or another side, so the motion is constrained to that plane, or hypersurface rather, and so we can get the third first order equation of motion. And I coherently used this letter 5 for generalized electrostatic potential. Well, so let's go to black holes in magnetic universes. The MKM solution, it means magnetized Kerr-Newman. It is obtained by applying so-called Harrison transformation, which is a generating technique, on a seed Kerr-Newman solution. As you look at the metric, it looks very similar to the original Kerr-Newman, but the appearance is deceiving because there's this lambda, lambda squared, and in fact lambda is quite complicated complex function which is constructed from nth potentials of the original Kerr-Newman, and it contains the parameter b, which can be interpreted as the strength of the external magnetic field. And well, if you look at this complicated function lambda, the dragging potential is even worse, and also the components of the electromagnetic fields, and that's what causes the complications. I'm not writing it here. But what also should be said about this space-time, it is non-flat asymptotics, which is which is quite undesirable, but it's so. When there is some interval of radii which satisfies this inequality, there is approximately flat region in that spacetime. It's not asymptotically flat, but we have some approximately flat region. But of course, if the magnetic parameter B is too high, this inequality cannot be satisfied, and we lose the astrophysical meaning of this solution. Well, and now let's consider we have two particles with some rest masses and form velocities, and we let them collide. In the instant of the collision, there is surely a frame where the total form momentum has just the zeroth component, which is the collision energy. We can take square of this expression, and then this is invariant. We can calculate it in any coordinates in any frame. And this invariant is called center of mass collision energy. And what we should do is to investigate its behavior depending on the selected curved background, parameters of the test particles, and the desired point of collision. Well, we have the general equations, first order equations of equatorial motion and the general collision energy formula. We can put them together and get very unwieldy result. But there is one interesting case when we take the limits of Leb's function going to 0, which means that we are approaching the horizon. It yields this formula, and what is interesting, that there are fractions in that formula. The fractions that contain parameters of the test particles. And if one of the particles possesses critical parameters which are defined by this constraint, the limit is unbounded. Let me note that just one of the colliding particles should have such parameters. The other one should be generic, or the numerator and denominator cancels, and the limit is finite. That can be better proven by asymptotic expansion. And let me also note that this limiting formula combines the results of Zaslavsky, who did a marvelous job in generalizing the BSW effect for arbitrary rotating black holes and also to charged black holes. Picture is better than 1,000 words, so let us say something about what are these particles with those strange critical parameters. But first we should look at the normal ones. I've chosen radial electrogeodesic motion in Reisner Northern to demonstrate this. And we have two types of particles. One type which goes from time infinity, crosses the horizon, goes to the region with singularity, crosses another horizon, and ends in a future time infinity of another asymptotically flat region. And another type which does not cross the horizon and avoids it. The critical particle is different. It does not have this symmetry with respect to the turning point as those two trajectories have. In fact, it asymptotically approaches the coordinate position of the horizon. That can be better seen from the effective potential. This is effective potential that tells us what is the minimum energy with that can particle move at a given radius. And when on the near the horizon, the n goes to 0, so this term is not here, and omega and phi go to the horizon value, and we get exactly this. So critical particle indeed has a minimum energy in the horizon. But what is important, if the derivative of this effective potential is positive or negative at that point, because that tells us whether the critical particle can approach the horizon or whether its motion is forbidden near the horizon. For MKM class, if we calculate the derivative of this effective potential, it turns out that there is a crucial factor which looks like that. And in some extreme case, this factor goes to infinity, plus infinity, as we approach the horizon, because R plus is bigger than M. And so all critical particles are kinematically inadmissible. They cannot reach the desired collision point from which we define them. So let us restrict to the extremal case when this factor is identically unity and the derivative of the effective potential is finite. To investigate which critical particles can reach the desired collision point, limiting collision point, and which not, I use the parameter space of the test particle, which is spanned by actual angular momentum, specific charge, and specific energy of those test particles. The condition for a critical particle defines a plane in this space. So and because this plane will be never parallel to epsilon axis, I used the projection of this plane onto LQ plane. Because of the magnetized black holes do not have flat asymptotics, we should not restrict to specific energy of unity, because specific energy is badly defined for large values of the magnetic parameters. And last remark on this slide, because of course we want to distinguish the sign of the derivative of the effective potential, so we should look for when it's zero. And this equation is quadratic in a specific angular momentum and specific charge. It defines a hyperbola in the parameter space. So let us illustrate the situation on the plot of the effective potential. Here we have two curves for the subextremal cases, and here's the desired energy level of unity. We see that the curves and the position of the horizon indeed reach the desired energy level, but then there is a forbidden band. The particle would be scattered by this ridge, and also for the higher value. But in the extremal case, we see that it is possible. It is possible that because the derivative is finite, it is possible that it can be negative, and the critical particle can reach the desired limiting collision spot all the way through, down to the horizon. So, and let's go to the hyperbola. This is that projection of the parameter space of this particle. Here is the specific actual angular momentum, and here is specific charge. And it is the critical plane that is projected so that there are values of energy in that plane, which looks like that. And here is the borderline, the hyperbola. Critical particles with parameters within this sector can approach the desired limiting collision spot on the horizon. The ones outside cannot. Let me mention that this value is interesting because the energy level of unity crosses this axis, so that below this value of spin on the extremal Kerr-Newman black hole, it is impossible for critical particles from rest at infinity which are not charged to reach the desired collision point. And Here is the result for a magnetized black hole. For stationary Earth, which is basically magnetized right to the North Stream, is the extremal case. And we see that for small values of the magnetic parameter, the curve is symmetrical, which is not surprising, because for rise to the North Stream without the external magnetic field, we don't have frame dragging, so there is no influence. There is no effect of the sign of the angular momentum, but as we go to higher values of the magnetic parameters, we see that the counter-rotating particles critical particles are preferred to be kinematically admissible. This is because there is a frame dragging with negative sign, which originates from the circulation of the pointing vector that is caused by superimposing of the electrostatic field of the black hole and the external magnetic field. Another situation is for a magnetized Kerr solution. For the pure Kerr, the borderline is just a straight line, because the behavior of particles does not depend on the charge at all, because the black hole is uncharged. But when we switch on the magnetic field, we see that the positively charged particles are benefited to reach the desired collision point. And let me summarize some employed techniques, mainly the near horizon limiting description. This was a good formulation of this technique is given by Bali and Horowitz. Basically, this generates a limiting metric that extracts information about the structure of the original black hole near its degenerate horizon. And for our purposes, it picks up the very information that we need to construct those diagrams. And the structure of the limiting metric is highly constrained, so that we found out that it's possible to describe a near horizon structure of extremal NKN black hole just by a suitable Kerr-Newman black hole, but with very complicated effective parameters. This indicates the Meissner effect without the necessity of calculating magnetic fluxes like Karas and Budinova did. That's all. Thank you for your attention. And for a case for treatment of critical particles in the static case is cosmological constant, you can see Jiří Daněk solved tomorrow.